Hello everyone, and welcome to the first lecture on reinforcement learning. So this is not your first machine learning class, right? So you have been looking at machine learning in the past, and typically when we talk about machine learning, so it's all about learning functions, right, from some input feature. It could be a vector, a numeric vector, or it could be images, as you see in this slide, right? Or it could be text, whatever is the input, right? So you are learning a function from the input to a specific output. So the output could be, categories as you see here, right? Or the output could be, real numbers like a temperature or predicted lifetime of a system and so on and so forth, right? So, but the crucial part of all the machine learning you have looked at so far, right, is that you are learning functions from input to the output based on examples somebody has given to you. So this is the classical setting that you have known as supervised learning, right? So take a look here. So you have images as inputs, right? So you have many different images that are given as inputs, and then the expected output is that you have to say it is an airplane. So somebody tells you this beforehand. Okay, I'll give you this training data where I give you samples and I tell you what should be the output given a particular sample. So based on this training data, right, we expect you to learn a function that when you are given a new sample, previously unseen sample, you should be able to tell me what the output is, right? In this particular instance, these are labels, or you could also talk about a case where the output is real numbers, right? So that's basically the point. So you are told beforehand, right? You can think of this as somebody giving you instructions as to how to give the output. What should be the decision that you are making, right, given a input. Okay. Of course, there is another variation of learning that you have looked at, which is unsupervised learning, things like clustering and so on and so forth. But there is really no output that you are expected to produce, but more like trying to figure out what the what are the patterns in the input data and so on and so forth. So that is another form of learning, but by and large, the bulk of machine learning that you have seen so far is in the supervised learning space, right? So I'm going to ask you this question. Right? So we talked about learning from data, but think about cycling, right? As a kid, right? How did you learn to cycle? Did you learn it from data? Right? Did people show you hours and hours of videos? I mean, you can go to YouTube, you can get 10,000 hours of videos of anybody doing anything in the world, right? You can easily get 10,000 hours of videos of somebody cycling, right? If I make you watch that repeatedly on loop, right, and then I give you a cycle, will you be able to get on it and go cycle? Most likely not, right? Because when you're trying to do cycling, right, the system is so complex. It's not that somebody can tell you, hey, turn left now, turn right now, push your right leg down, push your left leg down, and with all these kinds of instructions that you will learn to cycle. In fact, if somebody keeps shouting those instructions at you, you'll probably give up in exasperation, right? You'll never want to get on the cycle again. Right? Instead of that, think of how a kid learns to cycle, right? So typically, the kid gets on the cycle, tries a few things, it just wobbles around, it almost tilts and falls over, gets hurt. Or if the kid learns to balance and then stay on the cycle for a while, some uncle or aunt will clap and say, hey, good boy, well done, and so on and so forth, right? So it's getting some kind of a feedback, right? But nobody actually tells the child what it should do to cycle, right? They're told things, hey, careful, careful, don't fall down. So it's kind of very generic, feedback is what you get, but nobody actually tells you what is the output that is expected of you, right? So you have to learn through trial and error. You have to try a few things with the cycle. If you fall down, you get hurt, then that's not the right thing to do. You try to do something different, right? So this kind of a trial and error learning paradigm, right, is the crux behind what is reinforcement learning. We're talking about systems that are very complex, right? It's not something that you can very easily write down a control system for. Like, you can't write down what is the actual output that you should do, what is the action that you should take in a particular situation, right? It's very hard for you to write this down, and quite often we don't even realize what we are doing. In fact, if I ask you how you are cycling, right, you'll probably not give me an accurate description. So you wouldn't know, that you are throwing your center of balance one way or the other, and so on and so forth. All of those things you basically are doing in a subconscious level. So you won't even be able to describe things to me in an accurate fashion. right? So the main thing, even though again, just like in supervised learning, you are learning a function that takes an input to an output. So what is an input in this case? The input in the case of cycling is how much you have tilted from the horizontal, how fast you are moving, how much your handlebar has turned, and so on and so forth. That is the input, right? And the output you have to produce is, okay, how am I going to throw my body left or right? I'm going to push down with my left leg or my right leg. I'm going to turn the handlebar or not. So all of these are actions or outputs that you have to produce in response to the input that you are getting. So both supervised learning and reinforcement learning learn these functions from inputs to outputs, right? What is the crucial difference between the two? In supervised learning, somebody tells you upfront what should be the right output you produce for a given input, right? So we call this as instructions. So somebody is giving you instructions. On the other hand, in reinforcement learning, you try something, right? You get on the cycle, you try to move, you fall down, you get hurt, or you stay balanced and somebody claps, right? All of these things are after you try to do something, right? So these are like an evaluation of the output that you produced, not an instruction, right? In supervised learning, you are given instructions, and based on those instructions that are given to you, you kind of try to form some kind of an error gradient and then try to learn with that error information, right? Or on the other hand, in reinforcement learning, you try something first, and then whatever you try gets evaluated, right? But no one tells you what is the right thing to do. Okay, it's like writing an exam and getting marks, but you don't know, what is the right answer. In fact, it's even worse than that. You don't even know what is the maximum marks, right? You write an exam, I told you got a 5, but I don't tell you what is a 5 out of. So you don't know that, right? You have to try. It's like you have to do the exam multiple times, and every time I say, now you got a 5, now you got a 3.5, now you got a 4. Then you probably know, okay, 5 was really good, because whatever else I try, I'm getting only 3.5 and 4. Maybe I should do whatever got me a 5. This is trial and error learning, right? So if you think about it, so it's not just in cycling, right? There are a whole lot of different things that humans learn or animals learn, right? Which kind of falls in this trial and error paradigm. I think about walking. So I don't know how many of you have seen babies learn to walk. They're all of errors, right? I mean, so the babies keep falling all the time before they learn to stay balanced, and then they start walking, right? So a lot of trial and error, right? So before the success comes, right? So in fact, babies' bones are made of rubber while they are learning to walk, because they fall down so many times, nothing happens to them, right? They basically learn through trial and error. Nobody tells them how to walk, right? Likewise, take the task of talking, right? You all think that somebody trains you to talk? Maybe after you become older. But as babies, what are you doing? Babies just babble, right? They say ba 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 mama, and then suddenly it makes a sound that sounds like mama or amma or something like that. All the adults around the baby go crazy, right? They give it feedback. Positive feedback. Oh yeah, I made all the adults jump up and down. So let me try making the sound again, and then it goes. Then it says mama, amma, whatever. Right? So that basically babies learn through trial and error. The voice box is a very complex mechanism. Nobody can really teach you how to control the voice box, right? So you get feedback at a much higher level. So that's essentially some kind of a reinforcement learning is what happens when you are trying to learn to walk, talk, and a variety of other control problems. So what we will do in the rest of the lecture is look at a few examples, right, in terms of what are the typical tasks that people have tried using reinforcement learning for, right? And before that, a quick recap. So reinforcement learning is a trial and error learning paradigm. So one way of thinking about it is that it is learning from rewards and punishments, learning through rewards and punishments, as opposed to somebody giving you an instruction as to what to do. It's basically saying that, okay, if you do something, you give a reward. If you do something bad, you give a punishment, right? So if you think about it, that's how people train animals, right? So the roots of reinforcement learning actually goes to behavioral psychology, right? So it's learning about a system through interaction and through rewards and punishment. So it's some kind of behavioral training that people do to animals. So something that's where the roots go to, right? So some of you might have heard of Pavlov's dog, right? Some of you know of Pavlov's dog. So what does Pavlov's dog experiment say? It said that, hey, look, dogs salivate, right, when they see food. Why do dogs salivate when they see food? Because they are preparing to digest it. They think, I'm going to get the food, so let me get my saliva going so that I can digest the food easily, right? And normally, if there is a bell that is ringing, right? If there is a bell that is ringing, the dog doesn't respond unless the bell is very loud. Then the dog will start barking. So it's a nice little tinkle. The dog will just let it go. But what it will not do for sure is salivate, right? But then what Ivan Pavlov did was whenever he presented the food to the dog, he also started ringing the bell, right? Whenever the food is presented to the dog, the bell also was ringing. Right. So what happened? The dog learned to associate the sound of the bell with a reward, which is food. So the next time when the bell alone rang and no food was presented, right, the dog started salivating. So this is called behavioral conditioning, right? So you normally salivate at the sight of food, which is a primary conditioning, basically, because there is a real reason for you to do this, right? Because food, you need saliva to digest. So that is a proper causal linkage for that. But then you kind of get the secondary conditioning where sound of the bell makes the dog salivate. So this is learning an association between rewards and the input. So the input is the bell and then you salivate. So that's essentially where the root of this comes from, right? Of course, you can also think of the dog actually running an experiment on Pavlov. So this is a joke I like. So watch what I can make Pavlov do. As soon as I drool, he'll smile and make and write in his little notebook. So that's everything is relative. You can think of it that way as well, right? So why are people learning about reinforcement learning? It's not that reinforcement learning is new. It has been around from the 80s, and suddenly there is a lot of excitement about it, right? So why? Because reinforcement learning works. I mean, there are a lot of very, very interesting real world problems that reinforcement learning has started solving, right? And so we'll talk about some of these use cases as we go along today. But the most recent of the huge success stories of reinforcement learning comes from something that many of you might be familiar with by now, called ChatGPT, which was a system which used reinforcement learning with human feedback, like as a human is saying whether this sounds right or not, right, with some kind of a human feedback, using reinforcement learning to improve on the language generation model that was there. So that's one of the biggest success stories. Here we have many on the slide, and we'll talk about some of the more interesting ones as we go along. Okay. So the first thing I wanted to talk about is what are the instances when people typically end up using reinforcement learning, right? So when your system is very complicated, very complex, right? So much so that it's very hard for you to use classical ideas from fields like control theory or operations research to come up with a way of controlling the system cleverly, right? I mean, so one example people might think about is autonomous driving, right? And another example is like even things like cycling or controlling the temperature in a very, very large office building with like several floors and several rooms and several demands, different kinds of demands on this, right? Or you could even think of complex warehouse management systems, right? So where there are like hundreds of warehouses and thousands of stores, and you have to make sure that you are supplying the right products to the right stores at the right time. So all of these things kind of are very, very complex systems with complex dynamics, and writing down the right way of managing those systems or controlling those systems, right, using classical methods quickly becomes intractable, right? And in such cases, people have explored using reinforcement learning. So here is one fun example, right? So of a reinforcement learning agent learning to fly a helicopter, right? This example comes from several years ago, but it is still fun, right? So some of you might recognize the person in the picture, especially if you have been trying to look at some online machine learning courses apart from the BS course, right? That is Andrew Ng, and look at that. That's a helicopter that is doing. So that's a helicopter that is doing a trick flying, right? And it is trained using reinforcement learning, right? It's not a full helicopter that a human being can sit in, but it's fairly large. It's about the size of this table, right? Size of a normal writing desk. Right? And you can see that the helicopter is doing all kinds of trick flying and was trained using reinforcement learning. So the story is that when Andrew Ng was applying for faculty positions after finishing his PhD, so whenever he walks in to give his talk, he has a helicopter flying behind him autonomously through RL, and that's basically it. He didn't have to do anything after that. So it's an amazing example of how reinforcement learning caused to success. But the challenge with this was it took several years of engineering and a lot of resources to get reinforcement learning to do this. And for a long time, RL was more these kind of success stories were one-off, right? Where you needed to spend a lot of money to get these things to work, right? So second case where again I just wanted to show you some cool videos where reinforcement learning with complex dynamics was very successful is in this particular instance of humanoid control, right? So what happened here, and that person you see up there is Peter Stone. There you go. It's playing now. So Peter is a faculty in University of Texas at Austin, and he's one of the leading researchers in this field of reinforcement learning. But he also is one of the most successful people in this competition called RoboSoccer. So RoboSoccer is a annual competition that used to be very popular. Nowadays, it's gone a little lower in the popularity of getting robots to play soccer, right? So there were earlier, so everything was in simulation, and then people started to get four-legged robots, wheeled robots, and actual humanoids go and tussle it out and things like that. But here is a simulation humanoid thing, and you can see that this particular humanoid, right, is this team's the red team really is very good at scoring goals. I mean, you give it the ball from wherever in the field, it manages to kick it into the goal, right? So what happened? So the whole system was not trained using reinforcement learning. There's a lot of very complicated problems here, but which people have been studying for several years, decades even, right? So they managed to solve many of the problems like this walking, finding where the ball is, recognizing who your teammate is, and so on and so forth. Many of this can be solved using more classical control techniques or even supervised learning, right? But one of the things that they had a lot of trouble with was getting the robot to kick the ball. So what really happens is that the robot has to stand on one leg, right, swing the other leg, and then kick the ball, right? And then when it is far away from the goal, it has to kick it with enough force and in the right direction, right, so that it goes towards the goal, right, without falling over more often than not. So it turned out to be a very hard problem. So they basically pulled that problem alone out and made a reinforcement learning agent learn how to kick the ball, and you can see the results here, right? So it's like amazingly good at kicking the ball, and then it'll win with very embarrassing score lines. At the end of the tournament, Austin had scored something like 88 goals. Right? So it's like embarrassing. But then again, just to drive home the point that reinforcement learning is a great tool, but it is one more tool in your toolbox, right? It is not like it can solve every problem from scratch. So, but it's a great additional tool to have that allows you to do things which are not possible with other models of learning. I mean, there are certain things that only RL solves very well, right? So that's an example. So here's another example of a humanoid running, and this kind of a it's learning from trial and error, right? So whenever it falls down, it gets a punishment. If it runs, it stays balanced, it gets a reward, and so on and so forth. It turned out that they never gave it a punishment for this swinging its hand like that, right? It just looks like something very unnatural, right? The robot keeps on swinging its hand while it is running. It turns out that kind of gives a counterweight. The swinging of the hand is like a counterweight for the robot, so it doesn't fall. That swinging is actually helping it run. And because it was not getting punished for swinging, I mean, we will feel tired after a while if we keep swinging the hand like that. But since the robot was not punished for swinging the hand, it learned something that is very unnatural. But again, it learned completely from trial and error. It's not like a human being taught it. If a human being had taught the robot to run, they would have certainly not done the right. So complex dynamics is one part of it. The second thing is when you're operating in really complex spaces, right? So in fact, if you are instead of cycling in a plain empty road, if you're cycling in a more crowded traffic scene, or let's say you're trying to navigate in a very complex multi-roomed building that looks like a maze, right? Right, let's skip that and look like a maze. Or if you are trying to manipulate objects and the whole shelf is crowded with the various objects here, right? So it's not like you have enough room to very freely just go and pick up something and come out. So you really have to worry about maneuvering. So when it starts getting more and more cluttered and complex like this, then just writing simple rules or simple search engines becomes harder. People do solve it that way, but reinforcement learning gives a more convenient handle to work on. right? And then the other thing I want to talk about is like, so all of you know about probabilistic outcomes, probabilistic models, and stochastic systems, and so on and so forth. You have learned something about random variables and all that so far, right? So typically, when you are talking about what is happening in the world, right? So most of these engineered systems are not 100% accurate, right? So if I say that I'm going to move to XY coordinate, right, in some space, right, I have some space, I'm just going to move to the XY coordinate here, I'll probably end up within like 95% of that XY position. I might not get exactly where I wanted to go. So likewise, when I'm trying to look at something, right, and I'm trying to make a sense out of, okay, this is exactly where the object is in the space, I might be off by a couple of centimeters in terms of where I'm localizing the object, right. So here is an example. So there is the robot here. It's a simple robot. It's a simple robot here, which is trying to manipulate objects. There are two different bins here shown in red, and the robot is trying to put those bins there. And typically, it has some amount of uncertainty before it actually looks at things. It doesn't know where they are on the table and so on and so forth. So when the robot is just looking to the left, it doesn't know where the actual container is on the right, right? It doesn't know where it starts and so on and so forth. It basically has to look left and right multiple times before it knows where the containers are, and it can start manipulating the objects, right? And it has to put them into the containers. And likewise, it doesn't know where the objects themselves are and how to hold them. It has to look at things multiple times and try to grasp things multiple times. This whole uncertainty is there, right? And so what we did was we actually used reinforcement learning to train the robot to know where to look, right? So the work was called "Where Do I Look Now?" Right? So that's what the name we gave for this work. And the robot learned to manipulate these objects. And my colleagues who worked with me on this actually ran an experiment with humans later, and they found out that the humans tend to look at the similar locations, right? Like the robot was looking. They did not look for the same period of time because humans are slightly better at doing this kind of processing. But the qualitatively, the sequence of things that the humans look at when they are doing this kind of the same manipulation task, right, that the robot is solving, qualitatively the sequence of things the humans looked at was the same as what the robot learned to do through reinforcement learning. So it kind of tells you that some commonality there, though not quite there yet. And likewise, there are a whole bunch of other situations where you get both of this complex dynamics, complex workspace, and the stochastic systems, right? So where you have humans in the loop, and where you're trying to look at things that are very similar to how humans process information, right? So that's what cognitively motivated learning and so on and so forth. So a variety of instances where this appears, right? And finally, at least in this set, and then I have a couple of more after this, which is slightly more nuanced applications. I want to talk about one place where reinforcement learning is also being used in the industry and in other places extensively, right? So that is this problem of customization or personalization. So what do I mean by that? So here is a customization page, right? So this is a snapshot from Yahoo News. Okay, this is a snapshot from Yahoo News from a few years back, as you can see from the kind of stories that are here, right? But the set of stories that you see are basically customized based on who is coming to the page. So there are a set of editors who sit down and then decide that, okay, there are these 20 interesting stories in the world going on right now, right? Which 3 stories to show to this person when they come to the page? It depends on a whole bunch of learning that has happened in the past. And what is the feedback based on which you learn? Nobody is coming and marking saying that, oh, if Rahul comes to the page, then you have to show him these stories, right? I mean, nobody tells, or forget about Rahul. If a male from India who is age 20 comes to this web page, these are the stories you should show them, right? Nobody can sit and label, right? There are many problems here because every so often the stories are going to change, right? And likely every hour what is hot is going to change. And to say that a human being has to continuously label for the millions of different kinds of users who are going to come to your page and sit down and label which is the right stories to show to them, it just doesn't make sense, right? So what people did was set it up as a reinforcement learning problem. So they show a set of 3 stories, and if somebody clicks on a story, right, then they take that as a positive feedback, right? Or if somebody says, I don't like this story, I mean, sometimes you just say, don't show this to me anymore, kind of a feedback, right? If you give that, then they take that as a negative feedback. If you don't do anything and you move on, then it is basically no feedback. So using this kind of information, people started learning what is the likelihood, right? Somebody is going to click on a story. Right? And then when a new user comes in, you look at their, whatever features, okay, is that male or female, right? And are they coming from North America? Are they coming from India? If they're India, Bangalore or Madras. So like that, you look at whatever information you have about the user. What were the search queries? What are the last 5 search queries the user gave? And those kinds of information. And then you say, okay, if this is the user, then these are the 3 stories which have the highest probability of him clicking on it. So let us show those 3 to him. Okay, so that is how this whole customization, personalization bit operates. And this is actually the similar idea behind what is happening with systems like ChatGPT as well. Right? And the second case, instance of this kind of personalization is when people try to do ad selection. Okay? There's this whole field called computational advertising, right? So where people use many different techniques. I'm not saying reinforcement learning is the only thing that they use here. They use a whole slate of techniques to come up with the right ads to show you. It's a huge business, right? It's the only source of revenue for Google until recently. The only source of revenue for Google, right? So I mean, they get a lot of money through this. So this is a big money business, and so they have to be very careful about how they pick these ads to show to the user, right? So what do they do here? So once you go to Google, you type in some search keywords, right? And that's going to go and pick out, like 30 or 40 ads, right? That can be shown to the user based on the query that he has typed in, right? And then they start ranking these ads based on some metrics and so on and so forth. But still, there might be 5 or 6 ads you could show in the top place, right? How do I select which ad to show in the top place? Right, among these 30 ads that I have picked up? There you use reinforcement learning. Again, you use what is the probability that this person will click on the ad as your feedback, right? So that's what you're trying to learn. And so you look at, if you click, you get a reward of 1, right? If you don't click, then you don't get a reward. So that's basically what you're looking at, right? The ad selection process. Likewise, you could think about recommendation engines, right? Where you're talking about people recommending things like movies or books to people, right? And so it's quite often one of the mechanisms of choice to people, right? But then you might be thinking, right, really, what trial and error when you're talking about recommendation systems? Can't you do things like this, right? Customers who bought this item also bought, right? Or your recent history also bought. I mean, there are a whole bunch of different ways in which you can kind of suggest items to people. Why do you need trial and error here, right? Think about it. Customers who bought this item also bought. I mean, there are like 100,000 customers who probably bought that book, right? And they would have bought a whole lot more other things, right? I could think of some ways of scoring it, but I'll still probably end up with a fairly large pool of things that I would need to show you, right? So can I order them in some way and then show you the ones that you are most likely to buy or most likely to go and look at, right? So that is where reinforcement learning comes in, right? You can think of this as a trial and error thing that sits on top of everything else that you do to get your recommendation going. So that's basically the use of RL or RL like methods, RL inspired methods in the recommendation personalization space, right? Yeah. So and there are other things like this actually happens in many settings. So if you think of content or comment recommendations, right? So you must have seen in many websites. In fact, if 2 different people go and read an article, you might not get the same set of comments at the bottom of it. You see them reordered, and there is a nice reinforcement learning piece built into it, because people give thumbs up and thumbs down for comments, and so sometimes that just acts as your positive rewards and negative rewards, right? So people clapping versus falling down and getting hurt. So you get that already built in here, right? So the final piece as to why reinforcement learning and why reinforcement learning has become so hot recently, right, is because RL allows you to go beyond human knowledge to some extent. It allows you to go beyond human knowledge. How is that? Right. The first thing is reinforcement learning agents really do not need a human to tell them what to do. Right. In fact, you don't even, suppose I'm learning to play a game, right? Suppose I'm learning to play chess. I don't even need a human or another computer program to tell me how to play chess. I can just learn by playing against another copy of the reinforcement learning agent, right? So one of the earliest success stories here was by Jerry Tesauro back in the 90s, right? So there's this game called Backgammon, right? So Backgammon is a game where it's like Ludo. I mean, most of you know Ludo, right? So you have this four sides and then four teams, and then you basically roll a die and then you take your piece around the board. You can cut your opponent's piece and send them back to their base, etc., etc. And if the first person to get all the 4 pieces of the board wins, right? So that's Ludo. So Backgammon is like Ludo, except that it's a 2-player game, and you have a lot more than 4 pieces. You have 15 pieces per side, and then so that means that you have to be a little bit more strategic in making sure that you get all your 15 guys off the board before your opponent gets them off the board, right? So it turns out that it's not an easy game for an AI system to play, primarily because there is a die roll involved, and that makes the whole thing very complicated, right? So the number of possible moves that you can make in a given position depends on what are the different numbers you would throw in the die, and therefore using conventional AI techniques to learn to play backgammon becomes a little bit more challenging, right? So what Jerry Tesauro did was he trained a reinforcement learning agent to play backgammon, right, completely by self-play. Basically, it played against another copy of the program repeatedly. It played for several weeks, which is equivalent to several lifetimes of gameplay time for humans, right? It learned for several weeks playing against itself. And then in 95, we had a backgammon player that could beat the best human player back then. I mean, they played in a tournament, like they played in a series of 5 games, and the backgammon player ended up winning. Right. What is more interesting is that the RL player, which is called TD-Gammon, actually started playing moves that humans did not actually think were good moves, right? So some people were saying that, hey, these are not moves that you would find in a standard textbook, right? So these are not moves recorded by humans as good moves, and therefore when the RL agent learned to play these moves, people are a little confused, and this is the story that repeats, right? So after that. That came in the 90s. So till 2014, I mean, reinforcement learning was there. I mean, a lot of people are doing different things like Andrew's helicopter flying and so on and so forth. But then there's one big breakthrough that came in 2014, right? So somebody from this company called Deepmind trained a reinforcement learning agent to play these kind of video games. Like you can see these Atari video games. So you can see Pong, Breakout, Space Invaders, all of these games. I mean, at least when I was a kid, I have played these games. I'm pretty sure these are too simplistic for you guys. But they trained this agent to play these Atari games from scratch. So what do I mean by that? You looked at the screen, right? You get the pixels on the screen as input, and then you give joystick commands as output, right? You give joystick commands as output, take the pixels as input, and then if you score a point, then you get a reward. If you lose a life, then you get a reward or a punishment, and so on and so forth, right? That's all they had. So it literally learned from scratch. Nobody told it anything about the pixels it was seeing on the screen. So take the game of Pong, for example, right? So Pong, you have this green bar on one side, right? That is a paddle, and the agent, actually the reinforcement learning agent, actually controls the paddle, right? They can move it up and down, but you don't know that beforehand. The agent doesn't know that beforehand. So basically it tries moving the joystick in all kinds of manners, and then sometimes when it moves the joystick up, the green pixels move up, they move down. So from there it has to kind of figure out that, okay, if I want the pixels to move up, then I have to push the joystick up. If I want the paddle to move down, I have to move the joystick down, right? And it also has to learn things like that small dot there is actually a ball, and so on and so forth. Not that the reinforcement learning agent comprehends any of it in the way that you and I would understand how the game operates, right? But it needs to have some way of understanding the dynamics so that it can start learning to play the game well. Not only did it learn to play the game well, it started beating, beating human level performance. It started doing better than what a human being would score on these games, right? And it used a complex neural networks. All of you have finished the deep learning course by now, so you know that there are many complex neural network architectures. It used one such neural network. I mean, by today's standards, it used a very tiny neural network. But back in 2014, people were very thrilled that it managed to solve this problem. Right? And at that point of time, it was considered playing the Atari games from scratch was considered one of the hardest learning problems solved by a computer without any human input. Right? So that became a big thing, right? More importantly, what was different about this success story than what the others that you saw earlier, or some of those that you will see later, is that you could replicate this with very minimal investment. I mean, all you needed was like maybe one GPU to do the image processing, like one powerful computer, right? And then if you knew how to write code in Python, you can get the arcade environment, it's open source. You can get the ALE, download it, and then code up your algorithm and have it playing within a week. And you could replicate the success that Deepmind had on getting these Atari games to work, right? So this level of replication of a success story had never happened before the Atari game player came, and so that really triggered the new wave of reinforcement learning, right? And that okay, here is an example of. So let's show you some videos of how the game playing engine works, right? So you can see that at the beginning of learning, it has no clue as to what is happening. It just stands there. At this point, it has not even learned that it can move the paddle around in a reliable manner, right? So after some amount of training, so it starts playing a little bit, okay, but still not very good. And then after a while, it becomes very accomplished at playing. You can see the score that's happening now, right? So it's actually beginning to win on a very consistent basis, right? So the same approach is basically used for training multiple different games. It's not that it's the same solution, same neural network that's playing each game. Each game is being played by a different neural network, but it's able to look at that. It's learning to play, and then at some point it actually learns to keep scoring this and then do very well, right? So this is an example of the right way to play breakout, is that you drill a hole and then you get the ball to go through the hole so that it starts bouncing around on the top of the screen, and then it does the. You can see that, right? So that's a lucky run that it did, and then it learns a whole bunch of different games to play, and even though there's a lot more complex structure here, it still learns to play the Sequest, right? So I'll go on. I mean, so basically it learns to play all of these games, right? But then a little later, a couple of years later, came something that kind of completely blew people's mind, right? So there's this game called Go, right? You can see the Go picture on this side of the screen. So that's basically where there are the stones, right? What are called stones, are black and white things, and then you have these 15 by 15 square where you can arrange the stone. And it's a simple game as far as rules are concerned, but the strategies are mind-boggling. And the problem with learning to play Go as opposed to something like chess was that Go has a branching factor of about 250 on an average. So what do I mean by that? At any given point on the board, right, after you are in the middle of the game, you have possibly 250 different moves that you could make. Right? In chess, you have about 35 different moves on an average. So you can search through 35 moves and say, hey, okay, what is the right move to make now? But 250 moves, it just becomes impossible to do that kind of search. So you needed to come up with more clever ways of playing this, right? And for a long time, Go was considered something like a final frontier for AI. It's not like the rules were very complex, but there was this emergent complexity in terms of the strategies that you need to learn to play the game that were very hard, right? So this person in the picture, that David Silver, is one of the co-founders of Deepmind. So David led this team that came up with this agent called AlphaGo. Right? This came up with this reinforcement learning agent called AlphaGo, and then it became very good at playing Go. And it beat this Lee Sedol, who is a grandmaster of Go, not only is Lee Sedol any grandmaster, but by popular recognition, he was considered one of the best ever players of Go, because Go has this history. I mean, they actually have histories of games going back a century or so, right? So, Lee Sedol was considered one of the best players of Go in the history of the game, and AlphaGo ended up defeating Lee Sedol 4-1 in a matchup, right? So, what many people don't know is that one time that Lee Sedol won against AlphaGo was the only time a human being had actually managed to beat AlphaGo before that match or since. In actual tournament play, AlphaGo has always won 5-0 against humans, and that was the only time somebody managed to win a game against AlphaGo playing normally, right? I mean, now recently there are a whole bunch of other things that's been happening, where people are using AI systems to figure out what is the weakness of AlphaGo and then try to exploit it. But as a human being, trying to understand what AlphaGo was doing was like amazing. But remember, what really blew people away was things like this. I'll come back to the two slides I skipped. What really blew people's mind away was things like this, right? This is a very infamous move 37 from the second match that Lee Sedol played with AlphaGo, and the move AlphaGo made was so confusing to human beings. They never understood what the move was, right? So look at this. There's one commentator who said that's a very strange move, right? And another grandmaster who was there said, I thought the agent made a mistake, right? But Lee Sedol knew something was happening. So he thought and thought and thought. It took about 15 minutes for him to come up with a response to that move, right? And it turned out that that was the winning move. There was no way that Lee Sedol could actually come back from that move, and he ended up losing the game, right? But at that point, when the agent played the game, when the agent played the move, nobody knew, right, what it was doing. Everybody was confused. Then they started thinking, okay, there's some kind of extraterrestrial level intelligence in the room and things like that. So yeah, so all kinds of hype and other things started coming up. But this is really something that blew people away, right? And likewise, there are so many other success stories, playing strategy games in actual match play, right, and win against humans in a competition, not just one-on-one, but actually take part in the competition and win. And likewise, there's this AlphaZero, which is called a general AI algorithm, right, which can learn to play any game, right, as long as you set up the rules of the game beforehand, right. So it could play chess, it could play some other strategy game called shogi, and of course it could play Go, and it could solve a bunch of other things. And there have been further improvements to AlphaZero. There is another version of this called MuZero now, which can solve more problems, not just game playing, and so on and so forth, right. And the idea here is that at this point of time, we are completely learning through reinforcement learning. No human data, right? No human features, right? Just looking at the board position and then trying to play, right? And it's like amazing stuff, right? We'll come back and look at how some of this gets done, right? So we'll kind of demystify all of this and look at what basically the set of equations that are going to help you get there, right? So the other way that reinforcement learning agents go beyond human knowledge. I told you they learn this through self-play, so they're learning all these kinds of new strategies and so on and so forth. And some of this, which were actually developed for playing games, have actually been used for solving a whole bunch of other problems, right? So we'll look at those also later, right? So the other way reinforcement learning agents go beyond human knowledge is the way they can improve upon what are called heuristics. I mean, these humans have some intuitive notion of how a problem should be solved, so they kind of come up with a simple solution for that, and then RL can actually sit on top of that solution, use that solution to come up with a better solution through this kind of trial and error learning. So one example is when Google decided that they'll take the same AlphaGo like engine and try to get that to help improve their cooling efficiency. So as you can see from the figure, right, it reduced Google's data center cooling bill by about 40%, right. So this is non-trivial, because Google data centers take as much power as a small city, right, and if you can reduce that by 40%, it's like an amazing thing, right. So it turned out it actually learned a few non-intuitive rules that people are not using to control, right. Before this, they basically had this rule-based system that decided when to turn on cooling, when to increase it, when to drop it, and so on and so forth. but this RL based agent actually managed to improve it by more than 40%. Right. The other one that has gotten a lot of press is this program called AlphaFold, right. So AlphaFold solves this problem called protein folding, right. So you can see these very complicated squiggly structures in blue and green on the slide, right. So what these are essentially the 3D structures of proteins, right. So proteins are the building blocks of body, right, and typically you have a protein which shows up like a sequence like this, right. The protein shows up as a sequence, right, and then as soon as the sequence of amino acids are formed, they kind of fold into a very complicated 3D structure, right. And people have been struggling for decades to figure out what the 3D structure would be, so that you can actually form new proteins that will help you cure certain diseases, to understand what is happening in the body, and so on and so forth. And the sequence of amino acids, right, sequence of molecules that you have does not determine the property of the protein. It's the folded structure that actually helps determine the property of the protein, because some other whatever you are looking for, right, a particular molecule or a particular element that you are looking for could get folded into the structure, so that it is no longer accessible for any reactions, right. So if it's somewhere inside there, it won't react with the other compounds, right. So you want it to be on outside so that it can react to other compounds. So it's actually a very complicated problem. People from different disciplines have tried to solve it, right. In fact, robotics people have tried to see whether they can predict how a protein would fold, right. So all kinds of interesting things. So what they did was they took some existing protein folding algorithms, right, and then used their predictions as a starting point and used that to improve, and then they improved on that to come up with very good predictions for structures of protein, right. So basically when they did this the first time, when AlphaFold 1.0 came out, right, it achieved a 25% improvement over the best human effort. And people were saying, wow, I don't know whether humans should work on this protein folding problem anymore, so the AI seems to be doing it so much better, and so on and so forth. But they didn't know what was coming. So when AlphaFold 2.0 came, they basically 97% of the structures it was able to predict accurately. Right? So people started declaring that the protein folding problem is solved, right? And then instead of just having a protein sequence database, people started saying that okay, we should have a protein structure database, right? That's actually available now. So it's powered by Deepmind, so that the protein structure database is available and not just the sequence database, right? So luckily for people who are doing research in this area, it turns out that AlphaFold does make mistakes and there is still room for improvement, and you can use the predictions made by AlphaFold to build even more complex solutions. So it's not like it closed the research or it drove all the people in that area out of job. They're just solving more interesting, more deeper questions now. But it's still an amazing success story that built on top of a human solution, right? It didn't do this completely from scratch, but it still went beyond what a human could do, building on top of that solution. Right. A whole bunch of other applications that people have used reinforcement learning on. So we already talked about optimal control, we talked about robot navigation, but people have looked at for controlling chemical plants and other things, other kinds of, in fact there's a very interesting application that I know of where people use reinforcement learning to control conveyor belts in an airport. Right, in a very large airport in India, most conveyor belts in the airports don't work, so let's not worry about it. But in other places where there are a lot of different conveyor belts, the people actually have built these reinforcement learning based controllers to make sure that the packages come out in airports on timely basis, right? So interesting things. And then other class of problems where RL has had significant success and continuing to grow is in this area called combinatorial optimization, right? So things like scheduling algorithms, routing algorithms, right, and things like call admission control. So when does a cell tower accept a call? When does it drop it? And those kinds of questions, right? On the other side, remember I told you reinforcement learning has roots in psychology, right? Behavioral psychology. It turns out that there's a very strong basis in neuroscience, right? There's a lot of evidence that our brain does reinforcement learning. In fact, does specific forms of reinforcement learning. And so some people postulate that RL could be the primary mechanism of learning in certain parts of the brain, and so that has been developed in the computational neuroscience field, and both RL methods have fed into neuroscience, and neuroscience ideas have come back into reinforcement learning over here. So it's amazingly rich interaction that happens. Of course, psychology, as I already told you, right? And apart from looking at this kind of behavioral conditioning and other kinds of training domains, people have also looked at richer decision making models that are driven by what people do in reinforcement learning, right? And a lot more, right? There are things like intelligent tutoring systems which are personalized to a student based on RL. There is applications out there, and things like dialogue systems and chatbots and other things which are being trained using reinforcement learning, so to better serve the end needs of a customer.